So our project topic is systolic array with binarized matrix multiplication, and the team members include Jiahan, Kaiyuan, Yi, and Aditya. So matrix multiplication is an essential operation in many fields. For example, neural network, DSP, and computer vision. And traditional matrix multiplication, it can be both computationally intensive and consume a lot of memory. So it's really important to apply a more efficient computation method sometime. So binarized matrix multiplication simplifies it. As this example shown here, the binarized version just constrain all entries of the matrix to binary states, which is either +1 or -1. And to be more practical, you can just use 0 and 1 to represent these two states so that it will work better with binary hardware. So it's like this example here. We have two binarized matrices X and Y as input, and we perform normal matrix multiplication on it, and so that each entry in this outcome matrix is computed through vector dot product from the corresponding vectors. And so we adopted the approach from Lab 4, which is the vector product can be computed by this formula. And this allows us to perform the calculation only using XNORs and addition operations, which is much more efficient. And then we apply this binarization to the resulting matrix to get our final output. So here is our implementation of the binarized matrix multiplication without optimization. And it basically just runs through the whole matrix, and it computes this XNOR operation and keeps the running sum. And at the end, it does the binarization here and save that result into our output matrix. And for optimization, this matrix should be partitioned along columns, and this one should be partitioned along rows so that concurrent access to all elements needed for each dot product can be allowed.
So now to improve upon the baseline implementation, we developed a systolic architecture, which consists of data streams that push in the row and column data to multiple PEs at the same time. And these PEs are used to calculate the result of that index for the output matrix. And as we can see in the diagram here, C00 is going to calculate this PE is going to calculate the C00 of the output matrix. And the way it does this is by taking inputs A00, A01, A02, and similarly the B row inputs and accumulating that and storing it in the register. After the C00 is done processing the rows and columns, it pushes it to C10 and C01. And now C01 and C10 can parallelly perform the computation to get the result for their respective indexes. And this helps us parallelize the implementation, but there is an inherent dependency where C10 and C01 can only start calculating their values after C00 pushes it to the next cells. But we make up for this in the data reuse, since now each PE does not need access to the entire array or entire matrix. So this implementation is an output stationary design as mentioned before. Each PE is calculating one index while the inputs are flowing in and out used via HLS streams. So now how we implemented the C code for our systolic array is we have one processing element, that is the regular processing element, which all have two inputs and two outputs. And then we have our column and row processing elements, which have two inputs but only one output. And then the corner processing element that has two inputs and zero output. And we use the read and write functions for HLS streams, which have like a FIFO like buffer. And the PE size denotes how many elements the PE calculates in one iteration. For example, in a 8 PE size, it will read 8 elements, accumulate all of it, and then push all 8 elements to the next PE. So this is the representation where we first fill the input stream and calculate the systolic array binarized matrix multiplication, and then we get the result matrix. So this is how we assign whether a specific P is regular or the column or row based on its index and the size of our matrix. So if the index is 8 and the size of our matrix is 8, then we know that it's a corner P. But since it's also the output is also binarized, we have a final quantization step, and the way that is being done in the PE is we go check each register, and if it is greater than half of the max size, then it is assigned 1, and if it is less than half of the size, it's assigned 0.
As we can see, designing systolic array can be complicated and writing C++ code can be a headache. Now we have a project called Allo, which is developed in Professor Zhang's lab. Allo is a compiler itself. It's also an accelerator design language, which is pretty similar to Python, so that users can directly write a very coarse level Python-like code for their familiarity to implement a high-level synthesis. And here is an example of matrix multiplication written in Allo. As we can see, the syntax is pretty easy. And Allo has a built-in data flow module that can program data flow models, and it can be very suitable for designing systolic array implementations. And as we can see in here, we can de declare a data flow and use a mapping, and we can also use its get processor ID function so that we can avoid writing loops and directly generate all of the processing elements at once. And there's a very important part in data flow module, which is a pipe, and it has the stream type. The stream is a first-class abstraction that is essentially an FIFO structure, and we can get the element and put the element in a first in, first out, the first in, first out fashion. And here's the full code to generate a binarized systolic array design. And something worth to mention about is that we use some sort of auxiliary cells around LPEs, and they are used solely for communicating and passing data. And the internal processing elements are used for computing. And the corner ones are unnecessary, so we do not instantiate them. And as you can see, the full binarized systolic array can be can be filled in this one page, so uh it's quite easy to implement compared to C++. And moreover, based on the naive design, we also optimized the design by using three optimizations. The first one is tiling, and it can be used to improve the memory access because we're dealing with different Ps at the same time. And the second is that we can pack the data and to reduce the data latency transfer by using packing. Um, And as we can see later in the comparison, it has significant improvement over the naive implementation. And on top of data packing, we can unpack all the data in the processing element, and we can do all the computation in parallel by using SIMD vectorization. And to implement using high-level synthesis is essentially using loop unrolling.
Here's a summary of our result. As we can see that using systolic array is better than our baseline design, and using Allo is better than using Vivado HOS. However, with better latency performance, the resource usage required is also larger. Now I will demonstrate running our matrix multiplication design on the FPGA. And for this demonstration, I'm using input and output matrices of size 256 times 256. The reason for choosing this relatively large matrix size is to ensure that we can clearly observe the performance advantages and efficiency of our design on the FPGA. The bitstream file currently loaded on the FPGA SD card is our optimized baseline design. Let's first see the software performance on the Z board. Okay, the software execution time is around 4,000 milliseconds. Now let's see its performance on FPGA. As we can see, the FPGA execution time is much smaller than software. It's only around 1 millisecond.